Okay, so this is going to be Griffiths problem 1.5, part C, plus a little bit of some extra stuff. We're going to be finding sigma, plotting sigma over a wave function, and then calculating the probability of finding the wave function in a certain state. So here we go. We found in part B that the expectation value of x was 0, and that the expectation value of x squared is 1 on 2 lambda squared. Now, we want to calculate sigma so that we can put this over our wave function on the plot and see where we'll most likely find the state of our particle. So we're going to use the formula here that sigma is equal to the square root of the expectation value of x squared minus the expectation value of x quantity squared. Okay? And we know that this term is 0, so all we have is just the square root of 1 on 2 lambda squared, which is really just 1 on root 2 lambda. When we go ahead and plot sigma, we're going to be plotting sigma as the magnitude or the expectation value of x plus sigma, and then the expectation value of x minus sigma. X in both of these cases is 0, so we're just going to have plus or minus sigma when we plot it. If we take our result for sigma and go ahead and plot it, we end up getting this result right here. You can see our wave function in red from before. This time we used Desmos, not Mathematica. And we just arbitrarily set lambda, or L, called it L in this case, equal to 1. And you can see that this is, these two bounds, the purple and green lines, are plus sigma and minus sigma. And what we want to do then, in the last little add-on that we have here, is we want to calculate the probability that we will find something in the state of existing in this region right here. So if we have a particle and it's obeying this wave function, what is the probability that we will find it in the state of this region right here? Okay, well, that's fairly straightforward. Our probability is just equal to the integral of the region that we want to find something in times our wave function with t set equal to 0. And that's it. That's all we're trying to do. So what we can do is, if we go back here, we have two of these regions again where it can exist in this sort of state. So let's color in the other side. So it's everywhere that we're coloring in with red that we could find this particle in. And so you can see again, they're both equal. They're not necessarily opposite, but they're both equal. So we can just evaluate one integral and multiply by 2. So that's what we're going to do. And so that makes our integral 2 times the integral of 1 on the square root of 2 lambda times infinity, not times infinity, all the way to infinity, of the magnitude squared of our wave function here, which is going to give us lambda e to the minus 2 lambda x dx from parts A and B. Okay, we can evaluate this integral, and we're going to simply get the following: minus e to the minus 2 lambda x, evaluated at 1 on root 2 times lambda all the way to infinity. And when we do that, we're simply going to get an e to the minus 2 on root 2, which makes our probability that makes our probability approximately 0.243, or otherwise we have a 24.3% chance of finding this particle in the state of these red regions right here.